This video is about a variety of vector applications. The first one we'll talk about is the dot product. So the dot product, if we have U is A1, B1, and V is A2, B2, then the dot product is defined by multiplying the I components and then adding that to what happens when you multiply the J components. So we have A1, A2 plus B1, B2. Notice that the result is just a number. It's a scalar. It doesn't have a direction. It only has a magnitude. The dot product is a process that's useful in finding other things. I'll explain a little bit about what it can kind of be thought of, but essentially it's a pretty easy process. So if you take U and V as given in problem 1, find U dot V. So that's 2 times negative 3 plus negative 1 times 4. You get negative 6 minus 4, which is negative 10. So U dot V in this problem is negative 10. So what does that generally mean? We're going to just think about the dot product as multiplying with direction. So let's take the magnitude of one vector times the magnitude of the part of the other vector that's going in the same direction as the first. So if I just have A, B, C, D, and E all listed with all of their colors, so then hopefully it's easy to see. If I do A dot B, essentially what that means is I'm going to multiply this vector by this vector. And notice that they're going in the entirely same direction. So since the magnitude of A is 2 and the magnitude of B is 3, it would be logical to think that 2 times 3 is 6. So if I do this, 2 times 3 is 6, plus 0 times 0 is 0. I do get 6. Now A times C is going to be this red vector times this purple vector. So notice that they are going in entirely different directions. So it would be logical to think that 2 times 3 is 6. However, since they're going in entirely different directions, what we're going to end up doing is we're going to say 2 times negative 3, which is negative 6, plus 0 times 0. And we get negative 6 for A dot C. And hopefully that makes some sense. Now A dot D, we have 2 times 3 again, but these don't share any components. So the the red one is going entirely in the x direction, and the green one is going entirely in the y direction. So as a result, we would think that since they share no components, nothing is going in the same direction, and it's not even like they're going in opposite directions like the A and C. So A dot D, hopefully we get 0. So 2 times 0 is 0, and 0 times 3 is also 0. So A dot D gives us 0. Now what about if I have vectors that are going in different directions? So we have A dot E. Well, if I look at this pink one, what I see is if I break it into components here, what I would have is I would have a component of 2 going in the x direction and a component of 2 going in the y direction. So I would hope that I would get 4 because the components that are going in the same direction are 2 times 2. So let's see if that works. 2 times 2 is 4, plus 0 times 2 is 0. So A dot E gives us 4. C dot E, if I get rid of these yellow things and I move C over, then what I have is I have the purple one somehow getting in components like this. I probably should have left to the yellow. But I have a component of 2 and a component of 2. So notice that the 2 and the 3 are in the same their components are the same, but they're going in total opposite directions. So I would think that I'm going to get -6. So 2 times -3 gives me -6, and then 0 times 2 gives me 0. So C dot E is -6. D dot E, I'm going to look at what component is going in the same direction as the green one. And so notice that this purple 2, or I'm sorry, this pink 2 going up is going in the same direction as the green. So I'm going to have 0 times 2 is 0, plus 3 times 2 is 6, so the components are 6. So that's a bunch of dot product examples, hopefully to make some sense out of it. To find the angle between the vectors, you can use a dot product calculation. So the cosine of theta between two vectors is u dot v divided by the magnitude of both of them. So now we have an angle formula. So given 2 comma -1 and -3 comma 4, which was our first example, we're going to find the angle in between them. So the cosine of theta is equal to -10, which we found from the dot product on the first page, over 5 root 5. So we get -2 over root 5, and then we do the inverse cosine of that. To find an angle. So if we look, we see 2 comma -1 would look something like this, and -3 comma 4 would look something like this, and we see that it is a pretty big angle. So it seems to make sense. Now, if we just take one of these, for example, let's take a look at A dot E. So if I compute the angle in between them, I should know that it's 45 because I already looked at it and I have a really good idea that this is a 45-degree angle, but let's just confirm that. So cosine of the angle in between these things is going to be the dot product divided by the magnitude of both of them. So A dot E is 4. A has a magnitude of 2, and E has a magnitude of 2 root 2. So I end up with 4 over 4 root 2, which is 1 over the square root of 2, which is root 2 over 2. And I know that the cosine of theta equals root 2 over 2 when theta is pi fourths or 45 degrees. So that's just another confirmation of what we're seeing here. Now, some things that we'll be aware of. If the dot product is 0, the angle is going to be 90 degrees, and they're going to be perpendicular or orthogonal. So oftentimes we'll use orthogonal or normal as synonyms for perpendicular. If the dot product is greater than 0, we see that it's an acute angle. So notice that A dot E was 4. So we end up with an acute angle. And then if A dot E was negative, like CE or AC, we have a big angle. We have an obtuse angle. So we saw those earlier. And so that's kind of what we see. 90 degrees if the dot product's 0. If the dot product's greater than 0, we have an acute angle. If it's less than 0, we have an obtuse angle. Now we also have to be aware that the angle could equal 0 or could equal 180 if we have a positive or negative dot product, as we saw earlier. The projection of one vector onto another has the formula, the projection of A onto B. So that's read as projection of A onto B. So the bigger one is onto the smaller one. That's equal to A dot B over the magnitude of B squared times the vector B. So this is not a scalar. This ends up being a vector. And if we know, let's just take a look at what we see here. So if I look at this picture, the cosine of theta is going to equal the magnitude of A1 divided by the magnitude of A. So what I'm trying to do is I'm trying to figure out what is this vector. What is vector A1 as a vector, not just as a magnitude? So I know this. I multiply the magnitude of A to both sides. Then I'll multiply by the vector B, which gives me a direction, but it also gives me a magnitude. So how do I keep the value of this the same? Because I want to keep the magnitude the same. If I multiply by the vector B, I have to divide by the magnitude of B as well to keep it a unit vector. So I'm basically taking the magnitude of A1, then multiplying by a unit vector. And I do that on both sides of the equation. So if I multiply by a unit vector, it doesn't change anything. And then I also know this formula from the last slide. So what I can do is I can multiply the top and bottom of the right side by the magnitude of B. And then what I get is I get the dot product divided by the magnitude of B squared, and then I multiply it by a vector V. So that's the derivation of how you get this formula. So if I want to do that for these two problems, or for this U and V, I'll just take the dot product, which is 30 minus 10. So U dot V is 30 minus 10, which is 20. Then I take the magnitude of V squared. So that's the square root of 5 squared plus negative 5 squared squared. So it basically just gets rid of the square root. So that's where the 50 comes from. And then I multiply it by V. So I multiply it by 5, negative 5, the vector. So then I end up with 2/5, 5, negative 5. And I end up with 2, negative 2. So that's the projection of U onto V. And then if I want to write U as the sum of two orthogonal vectors, one of which is the projection of U onto V, I just figure out, I take 2, negative 2, and I add something in order to get it to 6, 2. So what do I have to add? I have to add 4 to the x and 4 to the y. So I would take 2, negative 2 plus 4, 4. And now I'm going to show that on Desmos and kind of show you what it looks like. On the screen, we have the vectors U and V. So U is in red and V is in blue. And our objective is to try and find the projection of U onto V. So what we're going to do is we're going to figure out if we cast a shadow of the red one onto the blue one, it would just be from here to here. And essentially what that means is it's taking dropping a perpendicular, dropping this at a right angle onto the vector that we're trying to project on. So this is projecting the red U onto the blue V. And so what we see is we have the vector negative 2, or I'm sorry, 2, negative 2. And then if we wanted to write U as a sum of two different perpendicular vectors, one of which is the projection vector, it would be 2, negative 2 plus 4, 4. So 2, negative 2 plus 4, 4. If we add the black and the purple dotted, we end up getting U again. We end up getting the red one. Finally, we're going to talk about work. In physics, work done by a force moving an object from some point to another point is defined as the dot product of the amount of the force times the distance from A to B in terms of a vector. So what we're going to do is we're going to dot the force vector with the projection vector. And our answer is either in foot-pounds or in Newton meters, depending on what units we're in. So if we take number 4, a wagon is pulled horizontally by a force of 20 pounds at a 60-degree angle. So if I look at the force is getting pulled with a 20-pound force. So there's a 20-pound force, and it's at a 60-degree angle. So my force vector is 20 cosine of 60 sine of 60. And then my distance vector is all horizontal, and it's 50 feet. So my distance vector is 50, 0. So I just take those and I do the dot product. So 20 cosine of 60 times 50 plus 20 sine of 60 times 0. Now this will go away because there's nothing moving in the y direction. Cosine of 60 is 1/2. So I have 10 times 50. This gives me 500 foot-pounds. So that's the work done in order to move this wagon 50 meters to the right or 50 meters horizontally if I'm pulling at this angle.